In this example, I have this, we're still on a frictionless surface. I have two boxes. One is sitting on the table and another is hanging over the edge. And the first thing it says is, what's the acceleration and what's the tension? So what I get from a lot of students at this point in time is you look at this and you're like, so which direction is it going to accelerate? And this is what's really important to think back to some of the first examples that we had. And I don't remember which one it was. I think it was, I had the one box, dirty up that piece. Let's do it here. I had the one box on a surface with an applied force going like that. And the comment I made on that example was there has to be acceleration. If I don't have any friction, the only force I have, if I draw out that free body diagram, so force gravity straight down towards the center of the earth, force normal, perpendicular from the surface, and then this applied force. So I have a net force. I have no option but to accelerate, because the sum of my forces then would give me my force applied equals mass times acceleration. So the same thing here. Don't let yourself freeze up over asking, well, I don't know which way it's accelerating. Is just to look at them both. And I look at this, I'm like, okay, so force of gravity is going to pull this straight down, and then this has this force of tension opposing that motion. So maybe that's not real clear right away. But when I look at this one, there is no tension. I'm sorry, no friction. So if there's no friction, that free body diagram, that's where free body diagrams are going to save your life every minute of every day in this physics class. So here's my free body diagram for mass 1. And I look at it, I'm like, okay, so the standard force normal, force gravity, and then my force of tension going that way. There is no force going to the left for this mass. There's nothing opposing that motion. So the only way I can accelerate is going this way. So my acceleration is going to go that way. And if it's accelerating that way and this rope is connected between the two, then that motion is going to be consistent for both. So then I'm going to have a net acceleration coming down. So I can go back and think in terms of the first question, or the last example that we did, which was just pulling the two. And on this one, I could ask myself the same question. Well, this line is continuous in connecting both boxes. So that means that this tension is going to be the same. If the tension is the same, then that means that the accelerations of these two must be the same. For fun, though, let's go ahead and write out our free body diagram number 2. And this one, let's see, in the Y, I have my force of gravity down and my force of tension up. And that's it. So this one is really important to define my axes. I am going to, I'm going to go to the right is positive and to the down is positive. Can you go to the down? To the right is positive and down is positive. Because I look at this and all of my motion is going this way, it's just going to make my math a little bit easier, so I'm not having to worry about losing any signs. Because now I can go ahead and do my summation of forces. So my sum of forces in the X, because this is free body 1 relating to this mass, is the force of tension will equal mass 1 times acceleration. And I'm going to go ahead and write the sum in the Y, just because it's kind of good for you to get practice on it. This is accelerating, but there is no angle. This is being pulled straight on the x-axis, so I'm not impacting this force normal at all. So what do I have? Down is positive. That's where I have to be careful. Force of gravity minus the force normal equals 0. They still equal each other, but they've changed signs. I come over here and I'm like, well, there is no sum in the X. It's all in the Y. So let's do my sum here. The only one I have to do is the sum in the Y. I've defined down as positive, so I have force of gravity minus the force of tension equals mass 2 times acceleration. Make sure that's clear. Cool. So this is asking for acceleration and tension. I can do the exact same trick that I did before, where I have my force of tension equals M1A. So I can take this force of tension because this is the same, they're connected. Well, it's not stretching or breaking. I can put that into that. Ooh, let's make sure that we are clear. So I have force of gravity 2. I'm saying that because it's related to mass 2. Minus the force of tension is mass 1 times acceleration equals mass 2 times acceleration. Huh. I'm kind of feeling like this looks very similar to the last example we had. Let's write this one out, why don't we, as mass 2 times gravity equals, moving this to the other side, mass 1 times acceleration plus mass 2 times acceleration. Now, once again, I'm going to factor out that mass. So I have mass 2 times gravity equals acceleration. I'm sorry, I'm going to factor out the acceleration. With mass 1 plus mass 2. And then this whole thing simplifies down to mass 2 times gravity divided by mass 1 plus mass 2 equals acceleration. So I'm betting you're asking yourself, well, I feel like we could have done the same thing and treated this as a system. And indeed we could. So let's think about this. Remember, for the thing on the flat surface, what I said is that there is a force being applied to that system, and that we're not worried about internal forces. We're only worried about something that is resisting that force. So let's take a look at this. What does this say? This says that this mass 1 and this acceleration, well, that is what's resisting this motion, right? So when I solve it, this is the force that is causing the acceleration. The masses are the things being accelerated. So in this case, just like the last thing, you're like, well, that tension is opposing it, but that's still an internal thing. So if it's an internal force, then it doesn't matter. It's not making this thing slow down. It's just this mass is actually what's keeping it or slowing it down. So preventing the acceleration. So that's the trick here, is that I could have, and what I have, what is the force causing that acceleration? Well, it was the force of gravity on mass 1. On mass 1. That's what caused it. That is divided by the masses that are being accelerated, and that gives me the acceleration. So I could have started with just 1, where I have my sum of my masses, and I have my force of gravity equals, this is mass 1 plus mass 2. Tension is an internal force. This is the only thing causing my acceleration. I have nothing externally opposing that. Pretty cool. All right, let's do one more.